Well, good morning, everybody, and welcome to our first micro app of the day. My name is Ben Zarlingo. I work for Agilent Technologies, actually in Everett, Washington, only about 20 or 25 miles north of here. So this morning, we're going to be talking about measuring agile and elusive signals, and since we have a fairly narrow time slot, and I don't want to be late, I'll get this directly underway. So the presentation this morning, a summary version of some longer material that's now available in an app note, but we're going to focus on agile and elusive signals. And in terms of measuring these signals productively, one of the things I'm going to pivot around is the idea of discovering signals versus troubleshooting and optimizing. The tools, the optimum tools, are often a little bit different that way, and so I'll show examples of both of those here today using two case studies that I think fairly represent a lot of the challenges in measuring agile and elusive signals. So one of the measurement case studies is going to be the ISM band at 2.4 gigahertz, and another one is going to be a scanning radar signal. We'll talk a little bit about the different techniques and tools, a little about the architecture and the advantages and disadvantages of these things. So first, let's get right to the 2.5 gigahertz ISM band. If you've looked at that band here at the show, you've seen it's extremely crowded. It's very heavily used, probably the most heavily used band like this worldwide. It's 100 megahertz wide. It uses some spread spectrum techniques of 2 or 3 different kinds. But importantly, it's very lightly regulated, and the signals that are sharing that band are not explicitly coordinated. There are some sense kind of routines, but it's sort of a free-for-all. Wireless LAN is the typically dominant occupant in this because it's the widest set of signals, the most common used. But there are other things, especially including Bluetooth, cordless phones, and then importantly, if you're concerned about interference, things like kilowatt or greater microwave ovens with sort of limited stability and certainly limited shielding. So it's a challenging band in some ways, and just about anything can be there if it suits the restrictions, or if it meets the restrictions of the band. It's very dynamic because of the lack of programming and sharing, so the content of this is not known at any particular point in time. So in that sense, it qualifies as a container of agile and elusive signals. And if you try to measure this with a swept spectrum analyzer, the traditional tool, the one you're most familiar with, there are some significant difficulties. Swept spectrum analyzers have some real benefits, especially because of their performance and familiarity, and their ability to independently adjust res bandwidth and span, and center frequency. But when you try to measure signals like this, sometimes you get pieces of the signal, sometimes you'll get all of it. Most often you get small bits of the signal or nothing at all, because even with a 1 millisecond sweep time, you spend a lot of time in retrace. The traditional technique for swept analyzers in this to see the signals is to switch to peak hold, either a short distance peak hold or a long duration peak hold. That has its own challenges as well, because some of these wider signals obscure some of the narrower ones, and they don't really reflect the dynamics of the signal, because you have the dynamics of the analyzer's sweeping res bandwidth filter. Of course, switching to the real-time spectrum or signal analyzers that were introduced a few years ago does provide a much better view of this signal. You're probably beginning to be more familiar with this display, this density display or cumulative history. It goes under several different names. But the idea is that the analyzer is calculating spectra, several 100,000 spectra per second. In real time, that is gap-free. All of the ADC samples are calculated with an FFT to produce a spectrum, a power spectrum measurement. And then those power spectral measurements are entered onto this bit array. The more often a particular pixel is hit, the brighter or the different color that pixel is. It gives you an immediate idea of how often something occurred. It doesn't give you any indication about time, but every 30th of a second or so, you update the display, and you get an idea of what has happened in the previous 5 or 10,000 spectra. Another way to look at that same data, though, is to use a single spectral combination for each display update, and then actually to go with a spectrogram display. The spectrogram doesn't tell you how often things happened, but it does stack up spectra at various rates to show you when they happened. So that's the other critical element in terms of understanding what's happening in a dynamic signal environment. And you can see in this case, the wireless LAN signals, the wide ones, seem to be sort of pulsed. You see some channel scanning going on here, and then you see some odd signals here, which may well be some of the microwave ovens we were talking about, or some other signal wandering through. You really don't have any guarantees in this band. This does give you a good idea of timing, and in the Agilent real-time analyzers, it can be combined with a power versus time display. So this is the envelope of the entire signal in the IF bandwidth. This can show you things like wide wireless LAN bursts and narrower Bluetooth bursts. So these are complementary displays. Each one of them has some pros and cons to it. But if we now change the time scale of this spectrogram, so the same sort of display configured a little bit differently, but instead of updating the spectrogram with one line or one trace for every trace update every 30th of a second, in this case, that acquisition time is only 1 millisecond. So we're throwing up about 30 of these traces each time. So our time scale changes, and we can start to see the pulses here for the wireless LAN. We can see a bunch of much shorter interspersed Bluetooth signals, and then some other interference that came across here. So by changing these time scales and by changing the displays, you can get a much better idea what's going on in this very agile spectrum. So the real-time analyzer views do have a number of really significant advantages, especially for agile and elusive signals. They're fast display updates. They'll give you a lot of data very, very quickly because they calculate so many spectra per second. They allow you to understand the signal or event frequency or the how often things happened or the timing of that. Especially useful in finding infrequent events or unexpected ones, the kinds of things that, as an engineer, keep you awake at night. They're really good at giving you some confidence that if something happened in a particular frequency band, that you'll see that, no matter how rare it was. But there are some limitations. Combining, since you can calculate spectra several 100,000 times per second, but only display about 30 a second, you're always combining those traces into one, or combining data into one. That blurs data together in terms of time. There's limited flexibility for these high-speed ASIC and FPGA-powered FFT engines. They don't give you the flexibility you have with the swept analyzer. Of course, there's limited frequency span. From 40 to 160 megahertz is the current state of the art in this. And their power spectrum. These are scalar measurements, though they may have a time axis. So I'm going to make a note here about what I'm not going to go to in detail, but we'll talk about a little bit more tomorrow afternoon in a different paper, and that's probability of intercept. I'm going to take, for this presentation, the informal approach of probability of intercept is the probability that you can see what you need to see in a reasonable amount of time with a reasonable confidence. That's kind of a qualitative thing rather than a quantitative thing, and the real-time analyzers give you much higher probability of intercept, but that's not the only way to get that. So as I say, tomorrow there's a micro app where I'll go through this with Ricky Overdorf's paper. I'll be presenting that in a little more detail. The other main thing that's done with these high-speed FFT engines that are processing all the data that comes through is to create a spectral mask trigger or a frequency mask trigger. Instead of triggering only on magnitude, in this case, you can examine each FFT as it's done, in this case about 300,000 times a second, test that against a mask, upper masks, lower masks, different logical behavior, and then use that to trigger a measurement, an individual display, or in the case of the vector signal analyzers, you can trigger a time capture. These masks can be made from the signal itself and have a lot of flexibility. They do have one disadvantage in that they're not time aligned. The trigger is generated from the mask every time an FFT is performed, so that is perhaps every few microseconds or so at the best. So there is some asynchronicity between the trigger timing and the actual event timing. There's another trigger in the vector signal analyzers that is time aligned, and that can be handy in a number of cases. I'll talk about one here today. So architecturally, I'm only going to go through a real quick overview just to mention that a lot of the hardware for real-time analyzers starts as the same super heterodyne swept spectrum analyzer, digital IF hardware that's become ubiquitous in the industry the past few years. But what happens is digitized data is then sent in either to capture memory or off to individual measurements. So it's a digital version of that part of the swept analyzer where we're not sweeping, where the LO is fixed. In the vector signal analyzers then, which again use the same hardware as the real-time and swept analyzers, the default displays look a lot like what you'd get from a swept analyzer, which is typically what you want. But a bit ago I mentioned something about probability of intercept. With the vector signal analyzers, you can use very, very large block sizes for your FFTs. So in this case, I used, I think, a 25,000 point FFT instead of a 1,000 point FFT, and I get much closer to a real-time measurement. I get much better probability of intercept. So by using this large FFT and one of several different advanced displays, we start to go from an infinitesimal probability of intercept up to just a few percent typically. And in many cases, that will actually show you what you want fairly quickly as well. It's nowhere near the 100% POI or near 100% POI that you might get with capture or with a real-time analyzer. But in many cases, just moving from tiny, tiny percentages up to a few percent shows you an enormous amount more of the signal and will give you an ability to see what you want to see. But the intersection between real-time analyzers and vector signal analyzers is what I wanted to deal with a little bit more today to help you make better measurements. Because the real-time analyzers are really good for that first task I described, that signal discovery task. But if you want to go further than that, to identify problems, to do things like demodulation or reprocess data, the vector signal analyzers have some real benefits there. So in this case, I've shown a little bit about what goes on in triggering here. The same architecture as before, but out of the DSP there is FFTs or magnitude calculations going on which allow us to do some triggering. And that's one of the ways to dramatically improve your probability of intercept. Use a mask trigger or use a magnitude trigger. Have the analyzer wait and process the data continuously until what you are interested in happens, and then capture that data and reprocess it. Capturing unusual events is really, really handy because it allows you to examine them, to do the troubleshooting, to move into other domains than power spectrum, for example. This shows some of the interface for triggering the frequency mask trigger. So in the vector signal analyzer, you actually have the same interface to the frequency mask trigger, and you also have the magnitude trigger. So the magnitude trigger is not frequency selective. It just looks at the magnitude of the signal in your IF bandwidth. But it has a benefit in that it's calculated sample by sample by sample, so it's time aligned with the signals that cause the triggering. That allows you to use some advanced techniques such as time averaging, which can dramatically and quickly improve your dynamic range. That doesn't apply for a frequency mask trigger where you're calculating triggers once every FFT, once every 1,000 samples, for example, or every 500 samples. Now, what kind of thing does that give you then? What I've done here, we're talking about the ISM band, I've done a time capture and then a playback of the ISM band. So now we can do playback with overlap, with complete flexibility in the FFT width, and we can start to see what's happening as these signals try to share that very dynamic spectrum. So for example, we can see the wireless LAN bursts, different powers, different timing. They almost seem to be coordinated here, and they may have a little bit of ad hoc coordination if they're smart enough access points. In this spectrogram, I've set two marker lines at 16.7 milliseconds apart because that's 1 over 60 hertz. And what that tells us is that, yes, these things wandering through the spectrum here, these are microwave ovens. And we can see some rather interesting things they do. For example, this one has a kind of a wide burst as it turns on, then wanders. There's another piece of its burst up here. We can see some Bluetooth signals here, and as a matter of fact, since we have complete visibility into this signal with time capture and playback, we can see this group of 5 Bluetooth hops here, here, and here. And as a matter of fact, we can see that here and here they're transmitted in the clear, but in this case, 4 of these Bluetooth hops are embedded in a wireless LAN burst. And this gets to the issue of using things like vector signal analyzers to solve problems, to point fingers, to assign blame, to optimize problems, or to assess their seriousness. So for example, using the vector signal analyzer, you can go back and individually demodulate this wireless LAN burst and look at the effects of the Bluetooth signal on that wireless LAN. Or with that same data, just a single capture, you can look at the Bluetooth bursts and demodulate them and look at the effect of the wireless LAN burst on Bluetooth. So those are the kinds of things that as an engineer you want to do when you find problems. And that's what I meant earlier when I said that the real-time analyzers are excellent for finding things, for the process of discovery. But in terms of tracking down those problems and optimizing them and understanding their seriousness, getting the rest of the engineering job done, things like capture and playback and that more advanced triggering can be really handy. I mentioned about demodulation. Another thing you can do with the vector signal analyzer is to change the center frequency and the span after capture. The same sort of thing you've been able to do with swept analyzers all these years, where you're making a measurement and you want to zoom in on a particular signal, filter out the other signals. In the case of the vector signal analyzer, you can do that after capture. So post-capture tuning and zooming allows you to identify particular elements of the spectrum and then demodulate those. So in this case, we have a bit of the ISM band here. We've chosen a particular segment in time, and then we've tuned and zoomed to center this signal and reduce the frequency span and demodulate the Bluetooth burst. So it may seem kind of advanced and a little bit obscure, but it's exactly the kind of thing that you're used to doing in a swept analyzer. You look at a broad spectrum, you find signals of interest, you center those signals, you zoom in on those, filter out the others. And in this case, we can go on and do not only scalar, but vector measurements and demodulation on those kinds of signals. Lastly, that same data, once you've grabbed the piece you want, or the whole thing, whether at its original center frequency and span or at a new center frequency and span, can be sent off to other devices. So if you capture a particular kind of signal, say one with some interference, wireless LAN with Bluetooth, you can send that off in digital form to things like MATLAB or SystemView. You can send that off to your prototype receivers in software. You can also send that out to real-world receivers in the version of RF hardware. So I don't have time to go through all of the details here today, but what I'm trying to summarize is that when you have things you want to do to solve RF problems, once you've identified the problem, those are the kinds of things where you'll typically move from swept analyzers to real-time analyzers for discovery, and then on into vector signal analyzers for identifying the problem and then using that data. The second example, a briefer one I wanted to go over, is a scanning radar. So in this case, this radar is sending out 7 pulses at a 10 megahertz separation, with a short separation between pulses and then a long separation between pulse groups. And then over a period of a few seconds, the radar antenna is rotating and we get narrow peaks as we hit the main lobes and then the side lobes of the signal. It looks like this in a real-time analyzer, and it's telling us about our 7 frequencies here, 10 megahertz apart. It's telling us the signals are fairly low frequency of occurrence. So this very quickly tells us a summary of what's going on in the signal, no matter how rare the events are. Much better than we get from a swept spectrum analyzer, where we have the dynamics of the signal and the dynamics of the swept spectrum analyzer confusing each other. And if we use that spectrogram, it gives us a time axis so we can see these peaks from the main lobe of the signal, and then we can see some pulses from lower side lobes. And if we acquire over a narrower period of time, we actually start to see the individual narrow pulses. But we don't really have the time resolution to understand what's going on there, and we don't have the separation in time. If we switch instead to a vector signal analyzer and capture, we can see 2 of these pulses. One here, an intergap or interpulse gap, and then another one. And we can do things like gated spectrum here to measure individual pulses. But the other main benefit of capture and playback in this case, if we capture the sequence of pulses, something that was obscure in all these other views, invisible in most cases, is now obvious. In this case, our pulse train does not start with the minus 30 megahertz pulse. It starts with the minus 20, minus 10, 0, 10, 20, 30, and then minus 30. So what's happened here is the fairly simple thing to do when you're assembling your signal. Your interpulse group interval, that delay, was put after the first pulse rather than before it. Simple error to make, but it'll confuse your radar, and you'll never see it in swept and most real-time modes. And yet when you do a capture and a playback, it's completely obvious. And now, of course, we can go back and individually demodulate those if they're modulated pulses. So that's the general point I wanted to make, was that all of these tools do work together. They can work together in the same platform. The architecture is the same. But what I think you'll find is that if you're worried about finding unusual signals, you're worried about spotting things like that you don't expect, real-time analysis is great. It gives you a very comprehensive view. It gives it to you very quickly because it's calculating hundreds of thousands of spectra per second, and it's not missing any data. But if you find a signal there and it's not obvious what the problem is, typically you'll move into things like vector signal analysis, perhaps on the same analyzer or on your PC, and do things like capture, playback, triggering, demodulation, full vector measurements, multiple displays, that sort of thing. So that's the short version of it. As I mentioned, we just released an application note on this that summarizes or that goes through this in more detail, gives some specific examples. I have about half a minute. I'm certainly willing to take questions afterward, and I'll be at the Agilent booth for the rest of today. So if you have questions, I'll maybe entertain one now and then more later if you have any. It was clear enough, I hope. Well, thank you all for coming.